In this video, I'd like to talk about work. Work is a physical quantity which applies when we move an object by applying a force to it. If a constant force F is applied to an object, which moves a distance d in that direction of that force, then the work done by the force on the object is defined to be the force times the distance. And therefore, the units of work are equal to the units of force times the units of distance. Now this is the same as the units of energy. Force times distance also gives you the same units of energy, which makes sense because the work done on an object is equal to the energy transferred to that object. So some typical units of all these quantities, force, distance, and work, are shown here. A typical unit of force in the imperial system might be pounds or tons or ounces. Typical units of distance would be feet or inches or miles, that sort of thing. And therefore the units of work would be foot-pounds or mile inches or so on. In the metric system, the units for force, the standard units of force, are newtons. The standard units for distance are meters or millimeters, centimeters, that sort of thing. And the units of work are joules, which we'll talk about in a bit here. Now let's first take a look at an example. If a 5-pound bag of potatoes falls to the ground from a height of 20 feet, then gravity has done 5 pounds times 20 feet, which is 100 foot-pounds of work on this bag of potatoes. This is because the direction of the force is downward and the motion was downward, and the force during that entire process was constant. Now remember, the weight of an object is equal to the force of gravity acting on that object. There is a source of confusion that arises when doing these problems, and it has to do with using the metric system versus the imperial system. When we use the metric system, it's much more common to refer to the mass of the object rather than its weight. For example, if you look at a 5-pound bag of potatoes, it says 2.27 kilograms on it, but that's not its weight, that's its mass. Newton's law tells us how to convert between an object's mass and its weight. Newton's law says that force is equal to mass times acceleration. And therefore, the weight of an object, this is the force of gravity on the object, is equal to the mass of the object times the acceleration due to gravity. Now near the surface of the Earth, this acceleration due to gravity is 32 feet per second squared, or 9.8 meters per second squared. So we can use this weight formula to go between mass and weight. Weight is equal to mg, where g is the acceleration due to gravity. So the weight of a 5-pound bag of potatoes in metric is found by multiplying its mass, which is given in kilograms, times its acceleration. And so its weight has units kilograms times mass per second squared, which may seem strange, but that is true. Now we define the unit 1 newton to be 1 kilogram times meters per second squared, and so this is 22.2 newtons. We also define 1 joule to be 1 newton times meter. So we see that the 5-pound bag of potatoes weighs 22.2 newtons. That is its weight in metric. But typically you don't see that. You see the mass given. Okay, let's revisit this example. If a 2.27 kilogram bag of potatoes falls to the ground from a height of 20 feet, then how do we compute the work done on this bag of potatoes by gravity? Well, work is equal to force times distance, because this is a constant force going in the direction of the motion. The force being applied is the weight of the bag of potatoes. That's its mass times the acceleration due to gravity. And again, this is only necessary to do because I wasn't given the weight of the bag of potatoes, I was given its mass. When we did this example the first time, I was given its weight, so I didn't need to apply force equals mass times gravity. Okay, so I don't need this parentheses. Now we can just plug in known information. The mass of the bag of potatoes is 2.27 kilograms. The acceleration due to gravity, g, is 9.8 meters per second squared. I'm using meters per second squared rather than feet per second squared because I'm sticking to metric in this situation here. And then the distance is 20 feet. Ooh, that's imperial actually. I want to convert that to metric, so let's do that. Okay, 20 feet is equal to approximately 6.096 meters, and here I've multiplied 9.8 times 2.27. And then we multiply that and we get 135 joules. Actually, we've made a rounding error here. You see, when I wrote 2.27 times 9.8 equals 22.2, that was kind of a lie. I was rounding there. And then when I multiplied by 6.096, I rounded again. So that was a bad idea on my part. What I should have done is save the rounding until the very end. Just multiply 2.27 times 9.8 times 6.096, and we get something which rounds to 136. Not 135. So the correct answer actually is approximately 136 joules to 3 significant digits. There is a fact that you should be aware of. The work required to lift an object some distance is numerically equal to the work done by gravity on the object if it were to fall back to its original height. This is just the weight of the object times that distance that it's being raised. For example, it takes 100 foot-pounds, or 136 joules of work, to lift a 5-pound bag of potatoes 20 feet, simply because of the computations we've already done. Now, there is a problem. Often we want to know how to compute the amount of work done by a force which is variable, not constant, or done on a body which is non-rigid. In other words, parts of the body might move farther than others. So in these situations, the formula for work that we've used does not apply anymore. This formula only applies when there's a constant force being applied to a body which is moved this single distance d. So how are we going to get around this? Well, we're going to use our recurring theme. We're going to slice up the problem into infinitesimal elements where a constant force is being applied to a body which moves a fixed distance. That is, the entire body moves this fixed distance. So then we can use the formula W equals F times D on these infinitesimal pieces, and then we can integrate to get the total amount of work done. To see an example of this, a space module weighs 15 tons on the surface of the Earth, and we want to compute the amount of work done in propelling the module to a height of 800 miles above the Earth. Now, this differs from the problem where we're raising a bag of potatoes 20 feet, because now, because of the extreme height that we're raising this thing, gravity is not going to be constant throughout the process. It becomes weaker the higher up we go. So we have a variable force, and we can't just use this weight times distance formula because the weight changes non-negligibly during the process. So we have to consider the fact that weight depends on height, so consider a snapshot where the module has been raised a certain distance and we want to raise it an infinitesimal distance. So the weight's going to be constant during that infinitesimal process. You see, if the height doesn't change very much, then we can consider this force to be constant. So let's let y be the distance that we've raised the module. Then the infinitesimal work done in raising it an additional height dy is calculated using the weight times distance. So the weight at height y, remember this will depend on its height, but here we'll put the weight after we've raised it at height y, and then we'll multiply that by the distance that we raise it, that infinitesimal distance that we raise it. Okay, to compute this weight, we need to use the following fact. The force of gravity between two objects is proportional, or inversely proportional actually, to the square of the distance between their centers of mass. So, since the Earth's radius is 4,000 miles, we should probably measure the distance we've raised the module in miles as well. Then we can express the weight of the module as follows. It is proportional, this is the constant of proportionality, k, inversely proportional to the square of the distance between their centers of mass. The distance between their centers of mass is the distance we've raised the module plus the radius of the Earth. And inversely proportional meaning we put that expression squared in the bottom. Okay, so since this is the weight of the object, we're still going to need to decide what this constant of proportionality is. This needs to be determined. And we can find that out from the given information. We know that the weight of the module is 15 tons on the surface of the Earth. That is when y equals 0. So plugging in that known information, we can solve for k. And we find that it's 240 million tons times miles squared. And therefore the weight of the module at height y is 240 million over y plus 4,000 quantity squared, given in tons. So the work done in raising it this infinitesimal distance dy is found by multiplying that by the distance, which is dy. And now we're ready to compute the total work done simply by integrating, where y is ranging from 0 to 800 because we were raising it from ground level up to 800 miles. Again, y is measured in miles. Okay, so now we can compute this integral by substitution. Let u equal y plus 4,000, so du is equal to dx. We can rewrite the integral like this, and I'm changing the limits of integration, so I won't be back substituting. Use the power rule, evaluate at the endpoints and subtract, and simplify. And it's 10,000 mile tons is the amount of work done on this module. To recap, we're just using our recurring theme. We're just slicing up the problem into infinitesimal pieces where a constant force is being applied to a body which moves a fixed distance. And we need the entire body to move that same fixed distance. We will then use the work equals force times distance formula on these infinitesimal pieces and then integrate to get the total work done. In the next video we're going to talk about hydrostatic pressure and force. But I would like you to try one of these work problems on your own. Hooke's law tells us the force required to compress or stretch a spring a distance x from its natural length. And it is F times kx, where k is a constant which characterizes the elasticity of the spring. A high value of k represents a very firm spring, a low value of k represents a very stretchy spring. Okay, so with this physical law in mind, I'd like you to answer these questions. First, suppose that we have a spring which takes 750 pounds of force to compress it 3 inches from its natural length, which was 15. I want you to show that the spring constant is then 250 pounds per inch. And then I want you to compute the work done to compress this spring a distance dx, having already compressed it x inches. And then I want you to integrate to find the work required to compress the spring from 14 inches to 9 inches. So give that a shot, and then I will see you in the next video.